Today, we are diving into a fantastic scientific detective story from the world of metallurgy. It's all about a time when trying to make steel stronger actually, and this is wild, made it weaker. Okay, so imagine you're an engineer. You're building massive things like offshore oil rigs or nuclear power plants. You need your steel welds to be absolutely incredibly tough. So what do? You add powerful alloys like chromium and molybdenum to strengthen it. But here's the crazy part. Instead of making the weld tougher, adding too much of these so-called strengthening elements was creating a brittle failure point. It was this dangerous paradox, and it had metallurgists totally stumped. So here's how we're going to crack this case. We'll start with the puzzle itself. Then we're going to shrink down to the microscopic battlefield where the real action is happening. We'll introduce a brilliant new theory, see how they tested it, look at the smoking gun evidence, and finally, uncover the deep chemical secret that solved the whole thing. So what was the problem really? Well, it all revolves around a very, very desirable crystal structure, a specific type of ferrite that was just behaving in a really strange way. The goal for a super strong weld is to pack it with a microstructure called acicular ferrite. It's tough, it's resilient, it's everything you want. But researchers noticed that as they added more of those trusted strengthening alloys, the amount of this hero microstructure actually went down, and in its place, a more brittle structure called Bainite was taking over. Why was helping the steel hurting it? To understand what's going on, we have to zoom in. I mean, way in. The answer isn't something you can see with the naked eye. It's a battle being fought between different crystal structures as the molten weld cools down. So let's meet the main players. First up, our hero, acicular ferrite. Now, the name sounds complicated, but just think of it as a chaotic, interlocking mesh of tiny little plates. This chaotic structure is its superpower. It makes it incredibly difficult for a crack to find a straight path, and that's what gives the steel its amazing toughness. And here's the rival, Bainite. It's the complete opposite of that chaotic acicular ferrite. Bainite forms in these neat, orderly bundles of parallel plates, and it likes to start growing from the edges, the boundaries, of the original hot crystals. Unfortunately, this orderly structure creates nice, easy pathways for cracks to form, which makes it a whole lot less tough. And that brings us to our mystery player, allotromorphic ferrite. For the longest time, this was just seen as a simple, kind of boring layer of ferrite that coats the original crystal boundaries when the steel starts to cool. It was there, sure, but its true role in this battle was a complete secret. So right here, we can see the whole battlefield. You've got the large original hot crystal. That's called an austenite grain. Now, Bainite, the rival, it loves to grow inward from that grain boundary. But what if something got in the way? What if that simple layer of allotomorphic ferrite could actually block the Bainite, leaving the entire inside of the grain open for our hero, acicular ferrite, to form? This was the beginning of a truly revolutionary idea. This idea eventually grew into a formal hypothesis. The scientists proposed something that was totally counterintuitive. Maybe that simple, overlooked layer of ferrite wasn't just a bystander. Maybe it was the key to the whole process. And there it is, the core idea, straight from the researchers themselves. They guessed that this allotriomorphic ferrite was acting like a gatekeeper. By coating the grain boundaries, it was physically blocking the Bainite from getting a foothold. It was like putting guards at the gate to keep the rival army out, which then allowed the heroic acicular ferrite to thrive inside the castle walls. It was a brilliant theory, but they still had to prove it. So how do you test a hypothesis like this? Well, you design an elegant experiment. The researchers came up with a really clever plan involving two different ways of cooling the steel, just to see if they could deliberately turn the gatekeeper on or off. The experiment was so simple, but so powerful. For the control group, they cooled the steel straight down. This rapid cooling wouldn't give that gatekeeper layer any time to form, leaving the grain boundaries totally exposed. But for the test group, they used a two-step process. Cool it part way, hold it there just long enough to grow that thin protective layer, and then cool it the rest of the way. If they were right, the two groups should look dramatically different under a microscope. And here's a look at that clever two-step heat treatment. You can see the initial high temperature and then that first hold. That's the magic step. That's where the gatekeeper layer is supposed to form. After that, the final drop to the transformation temperature is where the main event happens, the battle between Bainite and acicular ferrite. So the experiment was set. The samples were cooled. The only thing left to do was to look down the microscope. And what they saw was the absolute smoking gun they had been looking for. And wow, the results were just undeniable. On the left, that's the sample that was cooled directly. Just like they predicted, the grain boundaries are exposed, and the whole structure is filled with the weaker Bainite. But on the right, that's the sample from the two-step process. You can actually see the thin gatekeeper layer decorating the boundaries, and the inside is just packed with that strong, chaotic mesh of acicular ferrite. The hypothesis was correct. But wait, the story doesn't end there. The researchers realized it wasn't just a physical barrier. No, there was a deeper, more elegant chemical mechanism at play that made this gatekeeper so incredibly effective. So what's really happening at the atomic level? Well, ferrite can't hold very much carbon. So as that gatekeeper layer grows, it acts like a snowplow, just pushing all the carbon atoms out of it and into the austenite right next door. This creates a tiny, tiny zone along the grain boundary that is super saturated with carbon. If you look at the data, you can see this huge spike in carbon concentration right at the interface where the gatekeeper formed. And it turns out, Bainite hates high-carbon environments. It simply cannot form under those conditions. So the gatekeeper doesn't just physically block the boundary, it creates a chemical force field, a carbon wall, that makes it impossible for Bainite to even get started. That is the real secret to its power. So, to wrap this all up, we've gone from a dangerous puzzle to a really profound understanding. The paradox of stronger alloys making weaker welds was solved by discovering the role of this humble little gatekeeper layer of ferrite. This layer builds a chemical carbon wall that blocks brittle structures and lets the tough ones grow. The result wasn't just some academic paper. It gave engineers a brand new tool to design heat treatments in alloys to create precisely the microstructures they need, leading to stronger, safer steel for all of us. It's a powerful reminder that sometimes the biggest engineering breakthroughs come from understanding the smallest, most hidden structures. It really makes you wonder, what other microscopic secrets are just sitting there, waiting to be discovered that hold the key to building the materials of our future? Thanks for joining me.